The southern Milky Way holds, by current estimates, several hundred billion stars. Two of them, separated by 1.5 arc seconds on the sky, cannot be distinguished by a telescope with a 60 millimeter aperture. A telescope with 200 millimeters of aperture resolves them cleanly as two separate points of light. The physical reasons for that difference and what aperture actually controls in a telescope is the subject of this episode. Hello everyone, this is Farzad and welcome to the third episode of Austronomic. The aperture of a telescope is the diameter of its primary light collecting element. In a refractor telescope, that element is the objective lens. In a reflector telescope, it is the primary mirror. In both cases, aperture defines the circular cross-section through which incoming light enters the system. The quantity that governs photon collection is not the diameter itself, it is the area of that circle, of course. And that area relationship has a consequence that is easy to underestimate. Area scales with the square of diameter. When diameter doubles, area quadruples. When diameter triples, area increases ninefold. This is not a linear relationship, it is a quadratic one, and it governs how much signal a telescope accumulates for any astronomical source in a given integration time. Now consider an example. Consider ASCO 71F and Celestron HHD 800. These differ in aperture diameter by a factor of roughly 2.9. Because collecting area scales with the square of diameter, their light gathering power differs by a factor of just over 8 to 1. It means under identical conditions targeting the same object, the HHD 800, which is bigger than ASCO 71F, accumulates roughly 8 times more photons per second than the ASCO 71F. Aperture also controls a second physical property completely independent of light collection. That property is angular resolution. Angular resolution is the minimum angular separation between two point sources at which the telescope can still identify them as two distinct objects rather than a single merged blur. This limit is not set by the quality of the glass or mirror. It is set by something more fundamental. When a point source like a star is imaged through a circular aperture, diffraction spreads the light into a specific pattern. Diffraction is the bending of waves at the boundary of an aperture. It is a direct consequence of the wave nature of light, which we established in episode 2. The central concentration of light in the diffraction pattern is called the Airy disk, after the 19th century British astronomer Royal George Biddle Airy, who first derived its form. The disk is surrounded by a series of concentric rings of diminishing brightness. A larger aperture produces a smaller, more concentrated Airy disk. A smaller aperture produces a larger, more diffuse one. When two stars are close together on the sky, their Airy disks overlap. If the overlap is too extensive, the combined pattern is a single elongated smear, and the two sources are unresolved and not detectable as separate objects. The minimum separation at which the two disks remain identifiable is the angular resolution limit of the instrument. It is a direct function of aperture diameter and the wavelength of the captured light. The standard criterion for the angular resolution limit of a circular aperture is the Rayleigh criterion, formulated by Lord Rayleigh in the 19th century. It defines the minimum angular separation at which two point sources are considered just resolved. And by just resolved here, we mean the central maximum of one source's Airy disk sits at the first diffraction minimum of the other. At that separation, the combined intensity profile shows a dip of approximately 20% between the two peaks. a detectable but modest signature of two separate sources. For visible light near the center of the visible spectrum, this criterion produces a clean and practical result, as you can see on the screen. The physical consequence is an inverse relationship. Larger aperture, finer resolution limit. For example, if you double the aperture, the minimum resolvable angle is cut in half. Therefore, these two equations together describe the two independent physical roles of aperture. How much light is gathered in equation 1, and how finely spatial detail can be separated in equation 2. Both improve as diameter growth, but as the worked example will show, these two effects are limited by different factors in practice. Up to this point, resolution has been defined in terms of separating two sources. But the telescope also forms an image of a single point source, a star, and that image has a finite width. The image is described by the point spread function, or PSF. It represents how light from a single point source is distributed in the focal plane after passing through the optical system. For a diffraction limited circular aperture, this distribution is the Airy pattern. The Airy disks refers to the central region of this pattern, bounded by its first minimum. But it is not the only way to describe its size. There is another way to think about resolution. Instead of asking whether two sources can be separated, we can ask how wide a single point source appears in the image. This width is quantified by the full width at half maximum, or FWHM, of the PSF, expressed in arcseconds. The Rayleigh criterion defines when two such patterns can be separated. The FWHM of PSF describes the width of each individual pattern. Both arise from the same diffraction physics, but they capture different aspects of resolution. For a circular aperture, the diffraction limited FWHM is approximately 84% of the Rayleigh criterion, linking the separation of two sources to the width of a single stellar image. These distinctions become essential when the diffraction limited PSF FWHM of the instrument is compared with that of the seeing limited of the atmosphere, because atmospheric seeing is also measured as the FWHM of the stellar image in the same unit, arcseconds. Take the ASCO 71F with an aperture of 71 mm. Substituting into the resolution relation gives a Rayleigh limit of 1.94 arcseconds. The corresponding diffraction limited FWHM of the stellar image is approximately 1.6 arcseconds. This value must then be compared against the atmosphere. From Melbourne and surrounding regions, typical seeing produces long exposure stellar images with an FWHM between 2 and 3 arcseconds. The atmospheric blur is therefore broader than the diffraction limited image. Under these conditions, the final resolution is determined by atmospheric seeing rather than the telescope optics. This is the seeing limited regime. This condition is not specific to a single instrument. It applies across systems such as the ASCO 71F, ASCO 103 APO, and the Celestron HHD 9.25. As aperture increases, the diffraction limit becomes finer. However, on the typical Melbourne seeing of 2 to 3 arcseconds, this improvement remains below the level set by the atmosphere. As a result, increasing aperture does not improve the effective resolution of the final image under these conditions. What aperture continues to control is photon collection. A larger aperture delivers more photons into the same seeing limited image, improving signal to noise ratio, or reducing the required integration time. In this episode, we established that aperture determines how much light a telescope collects and the finest angular detail it can resolve. We then showed that under real observing conditions, atmospheric seeing broadens the stellar image beyond the diffraction limited width. As a result, the final image resolution is set by the atmosphere, not by the optics. Increasing aperture still improves photon collection, but under seeing limited conditions, it primarily improves signal rather than resolving finer detail. More details about this episode are available in the weekly journal in our GitHub repository for those interested. The next episode examines focal length, the parameter that determines what the telescope does with the light it has gathered.